If you see here, that is kind of a similar alkyl that we've been talking about. But on that side, we got a dark side, we got the ethanol, we got two different reagents, right? The dark side is a strong base. That is what makes E2 goes better because we have elimination, so let's think about substitution right now. That's a weak base. That probably better for the E1. So we have two reagent presence. One is good for the E2, the other is better for the E1. So the question is which reaction will take place? Is it E1 is going to take place or E2 is going to take place? We have two reagents capable of either in the solution together. So how are you going to choose? So this is a matter of the speed. You have a, I don't know how to make an analogy. Let's say you have a candy in the middle. There is a slow guy running through the candy. There's a fast guy running the same thing. Which guy is going to get the candy? Yeah, so it's the kind of same thing. You got strong guys, weak guys. Which one will do the job first? Strong one, because the strong one goes up first and then makes it fast. That's there as a slow one right now, but that's not complicated initially, even though it can probably make an E1 goes. But E1 goes because it doesn't get any other choice. It's not their preference. It's just waiting and nothing happens. And then when the carbocation forms, it can participate. It cannot participate directly from the beginning. So that's why the fast, stronger reagent will go through the first. I mean, if there's only that one available, not this one there, then yes, sure, the halogen comes up, carbocation forms, then of course we expect a rearrangement forming the most stable carbocation, and then that one, you need to think about two different adjacent hydrogen in the molecule. Either can be taken out, but you can have two different products because of one goes to the less substituted position, more substituted other ones. Sure, that will be the major products, but this whole discussion is moot. Because this is not the only reagent in the solution. We got strong one in there. Strong one will go to the job first. So don't just think about the other one, trying to work it out, because that takes time. If this guy somehow, okay, I'm not going to do anything this time, then yes, that will happen. But the molecule doesn't normally do that. When there's a chance, they just go for it. It's their instinct. So that guy is a strong guy. That's going to go abstract the hydrogen directly, and that will happen even before the carbocation forms. So that having a weak base present, it doesn't complicate the situation because the strong reagents will get the job done first. So either hydrogen will be taken out by the base, strong base, directly. That's an E2 mechanisms. And then if you pick out the hydrogen from this side, yes, you're going to have a double bond between those two. If you pick out the hydrogen from that side, you're going to make a double bond between those two. Those two are the E2 products. Which of those two will be the major products? Pretty sure that you know the answer by now, right? More substituted one. That's the only products that you're going to see. And obviously, that can be formed by the E1. Somehow, you just guessed this way, you may get the same answer, but somehow I would say that you're lucky in this case. But you need to know why things happening, how things happen.
So if we have a question like this on the test, and for some reason we do E1 instead of E2, will we get the same answer?
Yeah, I mean, you can just write down as an answer, but I wouldn't know how you process it. So that's why this question, you may get lucky.
So, well, when it's E1, do we have to draw the cation instead?
Yes, that's what is expected.
Okay.
Perfect. Next question is, there's a two molecule given here. Which one will make an E2 elimination go faster? How can you figure it out? They are kind of similar, right? Same structures, except this is a cis to dense isopropyl, that's a trans to isopropyl. That's only difference. So how can we figure it out? Well, you're gonna probably draw it out the most stable chair conformation, right? Cyclohexane doesn't exist as hexagon in 3D. It's gonna be cyclohexane and chair conformations. And then obviously, when you do that, the more the bulky one, probably the equatorial will be the best. I know this is not a TBUT, but still, that one going out to the equatorial means more than the method goes to equatorial. But anyway, since the trends, this is going to be equatorial, that's going to be equatorial. So that doesn't change. But where this chlorine is going to go, right? It's on this carbon. This is cis to that. So if the cis to this one is chlorine either axial or equatorial. Chlorine on this conformation is going to go for the axial or is going to go for the equatorial. It has to be cis, right? That's the clue that you should get it. That's the cis to this. So this is going to be axial. Trends to that is going to be the equatorial. So now you see the most stable chair conformations. Can you expect one of them going faster into elimination than the other? Because in elimination to happen, we need to have an anti-coplanar with adjacent hydrogen. That one, you see this chlorine, that hydrogen, they're lined up, they're anti. So anti-coplanar hydrogen is available on the most stable chair conformation. So we expect elimination happen. But the other one, can you find out any hydrogen anti-coplanar to this chlorine in this most stable conformation? You don't, right? Does not mean that it will never do EP elimination. It will just have to switch the conformation to another chair. When it switch to another chair, this thing will be axial, that will be axial. So probably that will be less likely to happen. So that's why it will slow down, because that conformation is a popularly available. It's not popularly available. So that's the reason. This is already at the lowest end conformation, which will take the most time in their life. This is not the right conformation for the elimination, even though it will stay most likely in that form. But when chair converts to another chair, then you can expect the elimination. But it will have to wait until it flips to another chair. So that's the reason this is a faster. You get the right, everything's ready to go at the most stable conformation, make things a lot more faster. So you can see the reason why I keep saying to you, as soon as you think about E2, what should be the pop in your mind? It's an anti-coplanar conformation. That really changed the things. As soon as you use the carbocation, you should really need to think about the rearrangement, right? All right, a similar question can be packaged another way. Let's say this is what you like to make it. Then what do you need to start from? It's kind of the same question, same thing, but I'm asking you to see the opposite way. Normally, we've been predicting what will be the products, but if you know the concept, you should be able to figure out what reactor you need to use to make that. The reagent was given, there's a strong base there. Don't be fooled by this. This is just there. But this is a weak base here, but that's not really complicating anything. Because the presence of a strong base, it has a bigger voice in here. That's an E2 elimination reaction. So what should be the first thing you should remember? E2 elimination reactions? Anti-coplanar. So how you make this one by the anti-coplanar? Well, let me tell you this. I will probably put the hydrogen here, bromine there, opposite side on the plane. That makes anti-coplanar elimination possible, right? Then I will populate these two based on what appears. These methyls and this hydrogen, let's say, is on here, right? We can probably put the methyl groups here, that hydrogen there. Where I should put this hydrogen? On the same side of benzene or the opposite side of benzene? On this part, I gotta put it there, right? These two are the cis. So elimination gonna happen this way. You're gonna base come, pick this hydrogen, you're gonna make a double bonds, bromine goes out, this is the anti-coplanar right there. If you got the phenyls in the back, hydrogen in the front, this hydrogen should be in the back, right? it should be the benzene, so they can be still the same side. This methyl should be opposite side of this, the benzene, so they can be trans in the end. So your geometry of the products is basically determining what geometry you need to have in the starting material to make that, so by the E2 mechanisms. So I'm pretty sure that this is not too difficult. You just need to remember that, E2 goes through the identical plane conformations. But you'll be normally doing this way, but this can also work backward too. What about this one? You want to make this one. I mean, this is not an elimination reaction, there's no double. There's a substitution here, and you're using the thiolate, sulfur with a negative charge, and then something called the DMF. Which one is the stronger reagent here? Is the DMF?
Yeah.
That sounds like a very strong, right?
Yeah.
That is this. That's the sulfur with the negative charges. DMF is a solvent, right? Remember that the polar 8-foot is over the good for the cyclic reactions. DMF is one of that. The structure of the DMF is actually less right down. You probably have to go like this. Find it. That's a solvent. That is not going to be doing any reaction. Don't be fooled by that. So that is a strong nucleophile. The sulfur with a negative charge, that's a nucleophile. So we're going to make a substitution on this carbon by the nucleophile. So this carbon should have a halogen. But something that you got to remember SN2 reactions. I mean, there's several things to remember. But SN2 reactions does invert of the stereochemistry, right? It's inversion of the stereochemistry of what you need to remember. Where is going to be bromine possibly here, but it should be the same as a wedge, or should we say it's a dash? Because it has to get inverted to become this. So we have to get the opposite, right? Not the same. So this is simple, but you need to remember this. That's the kind of part that we are asking you to figure it out. Bromine has to be there. That's kind of a thing that no-brainer because substitution happened on this carbon. So the halogen has to be here. But just the bromine there is not enough. We need to see the cell chemistry. Should be opposite to this one because that's the two reactions does inversion of the cell chemistry.